Okay. Hey guys, so today we're going to talk about the next unit is the quadratic formula, the discriminant, how if the nature of the roots. But I wanted to talk about before we get there. I wanted to talk about completing the square, because people are like using quadratic formula. I'm not a big fan of that anymore. So let's just talk about completing the square. And we're going to be talking about the nature of the roots. So the idea is, let's just talk about this. So you have a quadratic equation, right? You have x squared plus 8x plus 3 equals 0. And so you look at this, and your first instinct might be, I can't factor it. I wish I could, but I can't factor it. But I know there's two roots, and I can use the quadratic formula. And the quadratic formula, you have your first you set the equation equal to 0, and then you look for the coefficients of a, b, and c. A is 1, b is 8, and c is 3. And then you're like, okay, let me plug the numbers into the formula. So you say x equals, and what's the formula? I have a song, negative b plus or minus the square root of b squared minus 4ac all over 2a. So you have the quadratic formula, and you plug the numbers in. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And then you simplify this, so you get negative 8 plus or minus the square root of 64 minus 12, which is 52 all over 2. We know that take it to the side, we know that 52 is 4 times 13. So we know that we have negative 8 plus or minus 2 radical 13 over 2. Final answer, negative 4 plus or minus radical 13. And we know that we can solve this for anything. Let's just take care of the unit before I start going on about completing the square. We know, so the question is we have a parabola. So for the unit, it's given ax squared plus bx plus c equals 0. We know, we can use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? We know that this expression here is known as the discriminant. The discriminant. And it tells us a lot of great things about our parabola. We know that if b squared minus 4ac is greater than 0, then we know that the roots are not equal, right? And actually, if b squared minus 4ac, they're not equal and they're real. And if b squared minus 4ac is a perfect square, then the roots are rational. But IB doesn't ask that, but that's like an older thing. Anyway, so we have a parabola. If b squared minus 4ac is greater than 0, then we have a parabola. The roots are not equal and they're real. And once again, if the b squared minus 4ac is a perfect square, then the roots are going to be rational. On the second case that we want to look at, if b squared minus 4ac is equal to 0, well, we saw this in the last unit. The roots are, if b squared minus 4ac equals it, then the roots are what? Then the roots are equal, right? And rational. And what's the last case? The last case is when b squared minus 4ac is less than 0, and we saw that in the last unit that the parabolas kind of look like this. And so we know the roots are not real. And that means they're complex. Now, if you're in an SL class and you're watching this, we're really not going to investigate complex numbers. If you're in a higher level math, we have a whole unit on complex numbers. Get ready. Anyway, so you might get a question. The book asks questions like, you might say, given, x squared plus bx plus 9, for what values of b are the roots, the roots not equal and real. And you might say, okay, answer. You say, okay, well, if the roots are not equal and they're real, that means b squared minus 4ac is b squared minus 4ac has to be greater than 0, right? So you say, fine, b squared minus 4 times 1 times 9 has to be greater than 0. B squared has to be greater than 36. And so, how do we solve this? Well, I leave it like this. I say b squared minus 36 is greater than 0. I know that this is my parabola. This is the parabola b squared minus 36. And I know that when b is greater than 6, or when b is less than negative 6, then b squared minus 4ac is greater than 0, and that's when my roots are not equal and real. We can try another one. How about given ax squared plus 5x, 1 equals ax squared plus 5x minus 2, for what values? What values of a are the roots equal? Well, when are the roots equal? The discriminant is equal to 0. So you're like, so when b squared minus 4ac equals 0, write this down, and then you fill it in. 25 minus 4 times negative 2 times a equals 0. We have 25 plus 8a equals 0. And so a is equal to negative 25 over 8. And so the exercises are simply like this. They're going to give you a condition. You need to solve the right one, and then you're good to go. Yeah. Remember these inequalities. Once again, make it into a parabola. You have a parabola. Sketch the parabola, and literally look where is it above 0. Kids get weirded out. Kids feel like they have to do everything algebraically. You don't. Sometimes you can go back to geometry, and you're fine. Okay, and then the next thing I want to talk about, though, is I want to talk about completing the square. I want to talk about this idea of extending, the whole theme is extending algebra, geometry into algebra. So you learned in algebra 2. How are we doing for time? So you can stop watching. If you know completing the square, you don't have to watch this, but I just want to talk about this. So the idea of completing the square is a much easier way to help you solve equations. So for example, if you can manipulate an equation so like x plus 5 squared equals 16, this is great because I don't have to expand it and use an factor and use quadratic formula. Immediately, if I can get my quadratic in this form, I just take the square root of both sides. So I have x plus 5 equals plus or minus 4. X equals negative 5 plus or minus 4. The answers are negative 9 and negative 1. So the question is, how do we put it in this form? So let's start with the way you learn it. The idea was you have this expression, and the question is, I need to add something so that I can factor this into x. The idea is we're going to add on a term, and when we have that constant, we're able to nicely factor this into it becomes a perfect trinomial, and we can factor it into like x plus a squared. And so how do we do that? Well, in our teacher, maybe in Algebra 1 or Algebra 2, they took the geometry. They said, you know what? Let's take the square. Let's call that x by x. And then they introduced these rectangles, right? They introduced these rectangles that were, 1 by x. Right? And then when we so the idea is that there's x squared, 2x, so we had 1x, and then we would another one, so maybe we put it here, and we're like, no, let's put it down here, because we want to make a square, and we say, you know what? Now we have a square, and so it's x plus 1 by x plus 1, but what do we need to put here? And you said, we need another square. So that means we needed to add the square up here. Okay, right? Let's try another one. How about, x squared plus 4x? So we have our x squared, right? And we have our 4x. And you're thinking, okay, this is cool, right? You can put it like this. So I have x by 2. And then you do the same thing up here, x plus 2. And you're thinking, wait a minute, how do I complete the square? And I'm like, okay, clearly you need 4. Clearly you need 4, and so, you add the 4 up here. And that completes the square, and then you end up having x plus 2 squared. One last example, how do we do 6x? Because I only have 6 rectangles. Same idea, let's try x squared plus 6x. Given the square and the 6, what do we need to complete the square? And so you say, you can visually see what's going on here. You say, okay, well, it's x plus 3 by x plus 3. Right? And then you might say, well, and I need 9. Let's see if I have 9 yellows. Let's see, I need 9 here. 9. Yeah, perfect. So you're like, okay, I need 9. And then with these extra 9, I've completed the square, like literally completed the square. And so your x plus 3 squared, and so good. And so some of you might say, Mr. Adler, well, you're only using even numbers. But we know that there's odd numbers. So you might say, okay, how about like x squared plus 3x? Is that possible? Can I complete a square with that? And you're like, yeah, you think you can do that, right? You take this away, and then maybe I'm going to cut this in half. I'm going to cut this in half, right? So I have my square. I have 1 1/2, 1 1/2. That gives me my 3x. And the question is, what's going on in here? And you say, okay, that's no big deal. I can visually see what's going on there. I need my 1. I have my half and my half. That's another 1. And I have my quarter. And so it's x squared plus 3x plus 2 1/4, which is 9/4. 9/4. And so I end up with x. What is this? X by 1 1/2. X plus 3 halves. squared. And the question now is, so I can deal with odd numbers. Is there a rule I can come up with? Because we want to move out of geometry into algebra. And so you might say, oh, you know what? If I take how do I go from 3 to 9 over 4? You say, oh, you know what? If I take my 3 and divide by 2 and I square it, I get my 9/4. Does that work for my 3 rules? Let's check that out. Let me take my 2 and divide by 2 and square it. That gives me my 1. I like it. What's going on here? Take my 4 divided by 2 and square it. Love it. Perfect. What about that one? I can take my 6 divided by 2 and square it. Perfect. So that's the rule, right? That's the rule. And another thing, let's just point out something else while we're here. What's 2 divided by 2? That's 1. Not a coincidence. What's going on up there? What's 4 divided by 2? 2. Not a coincidence. What's going on up there? What's 6 divided by 2? Not a coincidence. What's going on over here? What's 3 divided by 2? That's not a coincidence. That's how you figure out what goes here. Now, so you say, okay, this is fine. But the next question is, how do we deal with negative numbers? And I've always been troubled, because I'm like, how do I use the geometry to represent negative numbers? And the answer is, I don't have to. I'm just going to extend this idea into the negative. Someone might come up with something for negatives. I'm not interested. This idea of taking things that I've developed in geometry and extending it to algebra. So let's see if it works in algebra. Let's see if this works. Let's see if, actually, I'm sorry, one last thing. What about, 2x squared plus 8x? Can I complete that square? And the answer is, yeah, just pull out the 2. And then you can just finish this up. Same thing, maybe it gets messy, because you're higher level students, you love fraction madness, right? So it's 3x squared plus 7x. Can I complete this to 3 squared perfect squares? The answer is yeah. Pull out a 3. And then we just have to complete this trinomial, perfect this trinomial. Take your 7/3. Divide it by 2, and then square it. Right? And this becomes 3 times x plus 7 over 2 squared. Perfect. Okay, now we want to go into negatives, but I'm not going to use the geometry. I'm going to see if I can extend the geometry into algebra into like negative numbers and see if that works also. Let's see if that works. So our first example will be x squared plus, minus 6x. Well, the rule was take the negative 6, divide by 2, and square it. Well, so it's x squared minus 6x plus 9. And the other rule, this should be the number in there, right? And so it actually turns out x minus 3 squared. It turns out the algebra works. We can try another one, x squared minus, 12x. What do we do? Well, the algebra says, take the negative 12, divide by 2, and then square it. Does this work? Yeah. X minus 6 squared. Everything still holds. So that's the idea. We're extending the geometry into the algebra. Now, you can obviously do some proofs. I wanted to take this idea of geometry, and then the same idea with 5x squared minus 11x. What do I do? Well, it's just algebraic trickery. Once again, pull out your 5. right? We know it's plus because we're squaring what we divided. Sorry. And then, yeah, so we have negative 11 over 5 divided by 2 squared. And then it becomes 5 x squared, x minus 11 over 10 squared. And we've completed the square. Personally, I'm a big fan of completing the square because it's going to make your life easier when we deal with all the complex numbers. So for example, the second you get a quadratic, I use completing the square. So for example, you have like x squared minus, 7x, equals 9. Well, you know what? I'm just, x squared. Let's make this a little easier. How about 2x? I'm making my life easier. I'm just saying, 2x plus 1 equals 9 plus 1. X minus 1 squared equals 10. X equals 1 plus or minus radical 10. Done. I don't use quadratic formula. And once again, I have my discriminant. I know what's going on here. You can try another one. 3x squared plus 2x equals, 5. Maybe this works out nice. I don't have to think about that. I can just divide everything by 3. Right? I can x squared plus 2 over 3x, take it to the side, 2 over 3 becomes 2 over 6, which becomes 4 over 36, which is 1/9, right? And so plus 1/9 plus 1/9. Once again, we're higher level students, so we can do this quickly. And then what do we have here? Well, I know that it's x squared, it's x plus 1/3 squared equals 16 over 9. X plus 1/3 equals plus or minus 4/3. X equals negative 1/3 plus or minus 4/3, which equals negative 5/3. Or 1. A little bit faster, but yeah. And so that's the idea. Once again, I like completing the square. I like moving at the pace. Last one we're going to see in a couple of units. If I say x squared plus 2x equals, plus 8 equals 0. X squared plus 2x equals negative 8. X squared, I know I have the plus 1 plus 1. And then I have x plus 1 squared equals negative 7. X plus 1 equals plus or minus radical 7. And then you see the final answer is x equals negative 1 plus or minus I radical 7. Okay, that's good. Anyway, thanks.